So let's look at the electromagnetic spectrum and reflection. So Newton discovered that what we call sunlight or white light is actually a combination of a whole bunch of colors, and he did this using a prism, and it's what you would call the familiar rainbow. So what he concluded was that white light wasn't actually white. It was a mixture of a whole bunch of different colors, and the prism separated them. So he called all these different colors a spectrum. So they kind of spread out different frequencies. Violet was the highest frequency and red was the lowest frequency, and they kind of spread out there. So Newton did that in 1665. Besides working on gravity and motion, he also explained a lot about light. So then Herschel was investigating many years later, more than about 130 years later, the temperatures of each of the colors of the spectrum. And so what he did was he did this experiment where he broke light up into its components, its spectrum, and he put thermometers on each of the colors, wondering which color was the hottest. And to his surprise, over here past red, where he couldn't see anything, there was really no light there at all. When the thermometer was placed there, it actually registered the highest temperature. So what Herschel realized was that the electromagnetic spectrum, the frequencies, didn't stop at purple and red. They continued going. Our eyes could only see from purple to red. But past red, there was another frequency which carried the most heat, and he called this sub-red or infrared. And it's the basically the start of the discovery of all the other parts of the spectrum. And so Herschel gets credit for discovering the infrared. There's also waves that we can't see on this end of violet. We call those higher than violet or ultraviolet. And that refers to, of course, the frequency um, when we say ultra and infra. So what we now know is that electromagnetic waves come in all frequencies. There's really no limit. It's like a sound wave. You can make a sound wave. You can shake a speaker back and forth at any frequency you want. It has to be between certain frequencies in order for us to hear it, but that doesn't mean you can't make higher frequencies. So just like that, light waves, which are produced by wiggling electrons, come in all frequencies, and the highest frequency is what we call gamma rays. And so these were rays from space. They can only be produced in nuclear reactions. They're extremely high energy. They're very damaging. And people thought they were something special. And now it turns out they're just a form of electromagnetic waves that are very high frequency. Slightly lower frequencies are X rays. Even lower than that, we call ultraviolet, so slightly higher than violet. And then there's this tiny slice of the spectrum of the frequencies that our eyes can detect, and we call that the visible part of the spectrum. And then if you go to lower frequencies than the visible spectrum, you get infrared. So these are waves that carry lots of heat energy. And then below that are microwaves and then radio waves. And all of our cellular technology and all of our communications happens basically in this range right about here, which is kind of what this one's showing. We divide the spectrum up into different names, but each technology uses a specific frequency. So 3G, Wi-Fi, Wi-Fi is actually 2.4 gigahertz. FM radio, so you guys know when you tune your radio, you're tuning it to a frequency like 90.1 megahertz. So those are all what we call the electromagnetic spectrum. It turns out that wave actually acts like, light actually acts like a wave sometimes, and it acts like a particle sometimes. We're not going to worry about the particle nature of light. That has to do with quantum mechanics. We're going to look at the wave characteristics of light. And when you characterize a wave, you can talk about its frequency, its speed, and its wavelength. We've already talked about the speed of light, and we know that's always the same in a vacuum. So we can talk about the wavelength and the frequency. So the wave equation, which we studied in a couple units ago, tells us the velocity of a wave equals its frequency times its wavelength. So that just tells us that for light, the speed, which is constant, always equals the frequency times the wavelength. So if the frequency gets bigger, the wavelength gets smaller. So the higher the frequency, the smaller the wavelength. So let's just do a little calculation. Suppose we're looking at microwaves and we want to know, hey, what are the wavelengths of microwaves? Um, you can you can look on the back of your microwave and you'll see that the frequency that your microwave uses in your kitchen is 2.45 gigahertz. This is the frequency which makes water molecules spin, and so that's it actually produces a resonance effect. Um, and this is the frequency of all microwave ovens because they're tuned to heat water. You can try it. Put an empty cup on one side, put a cup of water on the other side, run it for 2 minutes, and the empty cup is completely cold. It doesn't get hot. Microwaves do not heat the cup, they can only heat water. If something doesn't have any water in it, microwave can't heat it. Anyway, we want to know what is the wavelength of the microwave, this wave. So we know the velocity of the wave, it's 3.0 times 10 to the 8th. We know the frequency is 2.54 giga. Remember, giga isn't 10 to the 9. And we want to know the wavelength, so we can plug this in. The wavelength is the velocity divided by the frequency, which is 3.0 times 10 to the 8th divided by 2.45 times 10 to the 9th. And you work that out, and it's 0.118 meters. So, pretty small little wave. Now, when we talk about waves, we often represent them as rays. So if you have a wave and it's traveling a given direction, the wave goes up and down, up and down, up and down. So this would be like sort of the electromagnetic spectrum being wiggled. We can draw the ray showing the direction of the energy, the wave direction. So that's kind of the green arrow there. When we draw that, we call that a ray. So if I have a laser beam, the laser beam is sending out highs and lows of a wave, but I'm going to represent that by drawing a straight line, usually with an arrow on the end to show the direction, which is basically the ray of light, the direction the energy is transferring. So one of the things waves do is they reflect. When a beam of light hits a surface with lots of free electrons, these waves are reflected. So things that are shiny generally have free electrons, like metals. And the light comes in, it bounces, and it's reflected. And we are going to call the angle of incidence this angle right here and the angle of reflection right there. So we're not going to draw all the waves. We're just going to draw a line, a ray, showing the direction of the light's path. So here's the law of reflection. If you have a smooth surface and you have an incident ray of light, so incident means incoming. Excuse me. And the point where it contacts the reflecting surface is called the point of incidence. And we are going to measure all angles from the normal to that point. So if you have a surface, the normal is the line perpendicular to it. And so the light is going to bounce or be reflected like this. This is called the reflected ray. And we call this the angle of incidence. The angle from the normal to the light ray is the angle of incidence. And then the angle measured from here to here is called the angle of reflection. And get ready, it's going to be a tough one. Here is the equation which represents the relationship between the angle of incidence and the angle of refraction. Ta-da! That's going to be the easiest equation you ever get in physics. The angle of refraction equals the angle of incidence. That's called the law of reflection. There are two types of reflection. One we call specular reflection. You can think of specular as mirror reflection. So here the surface of the lake is super calm and smooth, and all the light bounces in an orderly way to your eye. And so you see a reflection of the chateau here in the lake. I believe this is Lake Louise in Banff National Park. Over here, the water's choppy though. And so when the water is choppy, you don't get a nice perfect reflection. All the light is still reflected, but it's reflected in all different directions. We call that diffuse reflection. So here's kind of what's happening. Specular reflection is when you have a very smooth surface and the light all bounces in an organized way and all the angles are exactly the same. Diffuse reflection is when you have a rough surface and the light bounces. It's all reflected, but it all bounces in different directions. It's scattered. So that's diffuse reflection. So this is specular reflection. This is diffuse reflection. A piece of paper actually reflects all the light that hits it, so why can't you see yourself in it? Well, if you look close up at a piece of paper, it's a whole bunch of fibers, basically wood fibers that have been pressed together, and it's not really smooth on a microscopic level. And so the light, when it hits it, it scatters in all directions, which is why it doesn't produce a nice shiny image like a mirror, because of the roughness. So those are two kinds of reflection. Okay, so Two things we're going to work on this one. We're going to solve some equations using the wave equation. So C equals lambda times F, and we're going to solve a couple problems using the law of reflection.